All right. Hi, everyone. Welcome to the next pandemic lecture of NETS 412. And I want to continue talking today about auction design. So at last class, we talked about the VCG mechanism, which was really remarkable for a number of reasons. We proved that it satisfied, in an extremely general setting, all sorts of nice properties. It was dominant strategy truthful. It was individually rational. It was budget balanced, exactly optimized social welfare. And so a reasonable question to ask after last lecture is are we done? Is there anything else that we need to do when we're studying mechanism design? And what I want to do over the next two lectures is point out some things that are lacking about the VCG mechanism. So we're going to talk about two things. And next lecture, we'll talk about the computational problem with the VCG mechanism, the fact that when we were deriving it, we didn't think at all about how computationally difficult it would be to maximize its objective. But today I want to talk about sort of a more obvious limitation, which is that when we defined the VCG mechanism, we were explicitly optimizing social welfare, this natural objective function which corresponds to making people in aggregate as happy as possible. But of course, that's not necessarily the only thing we might want to maximize. We might have a different objective function. And if we have a different objective function, then we're out of luck with the VCG mechanism. The VCG mechanism is just not the right tool for us. And so the question that I want to ask today is how far we can generalize the VCG mechanism, right? Is it the case that for every objective function we can write down, for every choice rule that we might decide upon, that we can pair it with some payment rule to recover all of the nice properties of the VCG mechanism? Or is it the case that somehow social welfare was special, that we can only get all of these nice properties for social welfare maximizing mechanisms? Or is maybe the truth somewhere in between? So at least one thing is sort of easy to observe, which is that at least sort of syntactically, social welfare is not the only thing that we can maximize. And here's a slight generalization that I'm asking you to prove on the homework, that you can actually use the VCG mechanism not just to maximize social welfare, which is just the unweighted sum of the valuation function of all of the agents for the alternative you choose, but you can actually use it to maximize any affine objective function, which just means rather than maximizing the unweighted sum of all of the bidders' valuations, you can actually differently prioritize the bidders, right? I can give a different non-negative weight to each of the bidders, and I can ask that the mechanism maximize this social welfare-like function, but now with weights, this weighted social welfare function, which is just the weighted sum of the bidder valuation functions. And if I want, in fact, I can even add a term that you can interpret as corresponding to preferences of the auctioneer, in addition to weighting the valuation functions of the bidders, these VI terms. I can add, an extra term, beta, which is also a function of the chosen alternative, and you can just interpret this as corresponding to maximizing some weighted social welfare function where the preferences of the mechanism designer also get incorporated. Okay, so on the homework, you're going to derive a modification of the VCG payment rule that makes the following objective function, this sort of affine version of social welfare, implementable in a dominant strategy truthful way. Okay, so all right, we can generalize at least a little bit beyond the objective function of the VCG mechanism. But what I really want to ask today is how far we can go. Like, can we completely characterize the set of things that we can optimize with guarantees of, for example, dominant strategy truthfulness? Okay, so on the homework, you'll show this simple generalization. What I want to do in class is characterize the whole class. Before I go on, we're not going to succeed, by the way, this lecture in characterizing everything we can do with dominant strategy truthfulness. Instead, we're going to restrict our attention to a simple but still expressive class of problems where we can get a complete characterization. But before I go on, this is a good time to ask whether anyone has any questions. All right. So we're going to restrict attention to what I'll call single parameter domains. So a single parameter domain, informally, is a setting in which I may not know bidders' specific valuation functions, but I know how everyone would rank order the outcomes. So for example, in a single item auction where I'm trying to, give out a bottle of Purell to the person who wants it the most, I don't know how much each person values the Purell, but I can safely make the assumption that everybody would prefer the outcome in which they get the Purell to the outcome in which they don't get the Purell. And single parameter domains are just sort of a generalization of this idea where I don't know people's particular valuations, but I know how they would rank order outcomes. And so formally, a single parameter domain, which is sort of a special case of the more general auction setting we've been considering, is one in which we have what I'll call a public value summarization function, which just maps the set of all alternatives to real numbers. Okay, and everybody knows what this value summarization function is. That's why we're calling it public. And so the only thing that we don't know about a particular agent's evaluation function is some parameter, some real number vi, okay? But I know that whatever vi is, your valuation for alternative A will just be vi times the value of your value summarization function. Okay, so this is getting at sort of settings where I already know your relative preference for the outcomes because I know this function w, which I can use to tell me, for example, how you would rank order all of the alternatives. The only thing I don't know is this multiplier vi, sort of the scale of your valuation function. Okay, so this is a simple class of problems, but still a relatively expressive one. So just to go through a couple of examples, single item auctions are single parameter domains, and the public value summarization function is a simple one. And it just says, well, for bidder I, they prefer getting the item than not getting the item. Okay, so the way I would encode that with a value summarization function for bidder I is I would say, okay, well, if the alternative corresponds to choosing bidder I, the value summarization function evaluates to 1. If it corresponds to choosing someone else, it evaluates to 0. Okay, and so I don't know how much you value the item. That's your sort of private value vi. But if you get the item, then I know that your utility will be vi times 1 vi. And if you don't get the item, I know your utility is going to be 0. But we can also represent sort of more complicated combinatorial domains as single parameter domains. So for example, the VCG mechanism, remember, operated in this extremely general setting. We didn't have to restrict attention to selling goods to users. And we talked about other things we could do, like choosing policies that would affect everybody. And it can also be used to represent procurement auctions. So maybe the bidders aren't trying to buy things. Maybe the bidders are trying to sell things. So for example, you could imagine that what I'm trying to do, what the mechanism is trying to do, is actually buy some path in a network. And the agents, the sellers, are, they correspond to the edges in the network. Okay, so maybe I want to, be able to route some network traffic from, provider A to provider B, and the owners, I'm going to have to buy bandwidth from the owners of different parts of this network in order to route my traffic all the way from A to B. And maybe what I want to do is buy the cheapest path, but I'd like to do it with a truthful auction. And again, in a setting like this, I sort of know that the agents in this auction, the sellers, they are going to experience some cost if they have to provide me service, and they're not going to experience cost otherwise. Now, I don't know maybe quantitatively what that cost is, but I know that they're going to experience cost if they provide service, and they won't otherwise. So again, if an alternative here corresponds to a set of agents that correspond to a path, then I can express this as a single parameter domain in which the public value summarization function for an agent corresponding to edge E is just 1 if his edge is contained in the path and 0 otherwise. Okay, and maybe one more example just to point out that these single parameter domains can still represent all sorts of things. Let's consider an online advertising problem. Okay, so suppose that the agents now, the sort of bidders in this auction, correspond to advertisers. And the alternative that I'm going to choose is going to correspond to assigning potentially a bunch of different advertising slots to different advertisers. So I'm going to partition my advertising slots to different advertisers, and think about these as maybe like, banner ads on websites like the New York Times or the Washington Post, things like this. Now, in a setting like this, I might imagine that the thing that the bidders value are sort of unique impressions. So maybe the thing that the bidders value are the number of people who see their ad. Okay, I don't know how much they value each impression, but I might hypothesize that whatever their valuation function is, it's going to be linear with some unknown scaling factor in the number of people who see the ad. Now, the number of people who see the ad, might not be a simple function of the set of advertising slots that I assign to a particular advertiser, because these different websites that I have slots on might have overlapping audiences, right? So maybe the Washington Post and the New York Times actually have highly overlapping audiences, but the Washington Post and Fox News have more disjoint audiences. And so if EJ is the set of viewers who will see the ad in slot J, then in this case, I could write down a public value summarization function for a bidder I and a particular alternative A, which will in particular map bidder I to some set of advertising slots J. And this would just be the cardinality of the union of the viewers corresponding to each slot that advertiser J gets, right? So we're not double counting people. This is just expressing the total number of people the total number of distinct people who will see an ad if I assign a particular set of slots J to a particular advertiser I. Okay, and again, this is a single parameter domain because I'm assuming that I know that the thing that the advertisers value is unique views and that their valuation function is linear in the number of unique views they get. And the only thing that I'm assuming that I don't know is their per view utility, this number VI. Okay, so these were just some examples. And now is another good time to ask questions if any of these examples are confusing. But the point here is just to illustrate that single parameter domains, while of course severe restriction compared to the set of all possible mechanism design settings that we considered last lecture, is still relatively expressive. It's not just single item auctions, but you can sort of shoehorn a bunch of different kinds of problems into this setting of single parameter domains. Okay, so are there any questions? All right. So the plan for the lecture, the thing that I want to do is completely characterize which objective functions we can optimize for if we restrict our attention to single parameter domains. So sort of the win that we're going to get by restricting our attention to this simpler class of mechanism design problems is that we're going to be able to come up with a complete characterization for everything that is possible to do, subject to the constraint of dominant strategy truthfulness. And a key feature of our characterization is going to be this notion of monotonicity. Okay, so what we're going to end up proving is that if the choice rule that we want to implement has a monotonicity property that I'll define in a moment, then we will be able to pair it with a payment rule that will make it dominant strategy truthful. And if the choice rule that we want to implement does not have this monotonicity property, then there's no payment rule we could possibly pair it with that would make it dominant strategy truthful. Okay, so this is going to completely characterize the set of algorithms, the set of choice rules that can be made dominant strategy truthful with any payment scheme. And it's not everything, right? So this notion of monotonicity is going to be really key to implementation with guarantees of dominant strategy truthfulness. And it means that dominant strategy truthfulness isn't going to come for free, right? Like we might have thought after seeing the VCG mechanism that, whatever you want to do algorithmically with an appropriately clever payment rule, you can do that thing and make the mechanism corresponding to your allocation rule and your payment rule dominant strategy truthful. And what the characterization we're going to prove today says is that that's not true. If you want dominant strategy truthfulness, you have to limit your ambitions a bit, or said another way, you have to figure out how to do what you want to do with this monotonicity property. And this is something that's going to end up being really important when we think about dealing with computational complexity constraints, the way we will next lecture. Okay, so what is this monotonicity property? So it's some property of a choice rule. Remember, a choice rule is just the function that we get to design that takes as input everyone's reported valuation and then chooses an alternative. And we will say that a choice rule for a single parameter domain is monotone non-decreasing in the bid, in the reported valuation VI of some bidder I, if no matter what everyone else reports, and for every alternative report VI prime that is bigger than VI, then when I look at the outcome that results when you report the higher valuation VI prime, you should only be happier with that outcome compared to what would have resulted if you reported the lower valuation. Okay, so let's just sort of parse this again and remember that the choice rule X, when we plug into it everyone's reported valuations, spits out an alternative. And WI, the public value summarization function, is encoding for us person I's relative preference for the different outcomes. Okay, so if WI is higher for one outcome than for another, that means that person I is gonna get higher value for the one outcome compared to the other. And so remember, VI prime is a bigger bid than VI. What this is saying is that if your choice rule is monotone, what that means is exactly that if you raise your bid, the only thing that can happen is that the alternative that's chosen is one that is more preferred for you. Okay, so an allocation function, a choice rule that satisfies this monotonicity property means that simultaneously for all of the bidders, they can only be happier with the alternative chosen if they raise their bid. So the choice rule is sort of happiness monotone in everyone's bid. Okay, and this sort of corresponds to a pretty natural and simple condition if we think about it in the context of single item auctions, which is maybe helpful to build intuition. And all the monotonicity property says when we sort of specialize to single item auctions is that by raising your bid, you can never go from winning the item to losing the item, right? So in single item auctions, you're happier when you win the item than when you lose the item. What this says is that as you raise your bid, it might be that at some point you go from losing to winning, but you can never go from winning to losing. Okay, it's sort of a natural thing. The choice rule that tries to give the item to the person who values it the most, that is a monotone choice rule, right? Because if you raise your bid, you only move yourself forward in sort of the rank ordering of the bids. But if I tried to, if I wanted to consider the choice rule that gives the item to the person who values it the least, or the person who values it the second most, those wouldn't be monotone choice rules, because in all of those cases, it might be that if you raise your bid, you go from, for example, being the lowest bidder and getting the item to being the second lowest bidder and no longer getting the item. Okay, so hopefully that makes sense, but ask away if this concept isn't clear, because this is sort of going to be the crucial thing that we reason about today. All right, monotonicity. Okay, so the theorem that we want to prove is that monotonicity, in the sense that we just defined, is both a sufficient and necessary condition for dominant strategy truthfulness, which is to say, if the algorithmic problem that you want to solve corresponds to a monotone choice rule, then you're in luck. There is a payment scheme out there that when you pair it with your preferred choice rule will make it a dominant strategy truthful. In fact, it's a payment scheme that I can generically define, and so for each new application, you don't have to think of a completely novel, clever payment scheme. Once we prove that this generic payment scheme makes any monotone choice rule truthful, then if you have a monotone choice rule, it's just going to be a matter of chugging through some calculation to figure out what the corresponding payments are that make it truthful. On the other hand, if the algorithmic problem that you want to solve corresponds to a choice rule that doesn't have this monotonicity property, then what we're going to prove is there doesn't exist any payment scheme at all that makes your choice rule dominant strategy truthful. And so that means that if you find yourself in that situation, you either have to decide to solve a different algorithmic problem, right? Maybe instead of solving whatever problem you wanted to solve exactly, you have to back up and solve some approximate version of that problem that recovers monotonicity. Or you have to give up on dominant strategy truthfulness. Okay, so this will be an important property. And so here's the theorem. Okay, and here's sort of what we're gonna spend the rest of the class proving. And it's the following. So for any single parameter domain, a choice rule X can be made dominant strategy truthful if and only if X is monotone non-decreasing for all of the bidders. And if it is, then here's the payment rule that makes it dominant strategy truthful. The amount of money that we are going to ask bidder I to pay is equal to, well, let's look at this first term here, VI times WI of the alternative that's actually chosen. This is just bidder I's valuation for the alternative that was chosen. So this is how happy buyer I is for the alternative that we chose. Okay. Minus something. Okay, minus something non-negative. So first of all, we can already observe that this is going to be an individually rational payment scheme because we're never going to ask anyone to pay more than they value the item for. We start from the amount that each person purported to value the alternative that we chose, and then we subtracted something off of it. Okay, so I never ask you to pay more than you're willing to for the alternative that we chose. And how much are we going to subtract off of it? Well, it's this integral that might at first, not look super intuitive, but actually sort of is. So first, let's just, read out what the integral is. But then let's, again, think about what it means in the setting of single item auctions where this will actually make a lot of sense. Okay, so what is this thing we're subtracting off from your value for the alternative chosen? Well, remember, your public value summarization function tells you how happy you are for the alternative that's chosen. Now, we are integrating something from 0 all the way up to the bid that you made. Okay, we're integrating this variable z, and what we're doing with z is we're sort of asking the counterfactual, what alternative would have been chosen had instead of bidding VI, you instead bid Z, keeping everyone else's bids fixed? Okay, that would have potentially led to a different alternative had you counterfactually bid Z, something lower than your true valuation. And we're evaluating these counterfactual alternatives that were actually chosen with your, remember, monotone public value summarization function. So remember, the monotonicity property is going to mean that you are less happy with the alternative chosen if you put in a lower bid. Okay, so as we integrate Z from 0 up to your real bid, WI will be some increasing function ending at your relative happiness of your actual bid VI. Okay, so that's some integral. It's a little confusing, but let's just think about what this payment scheme corresponds to in the case of a single item auction. So remember, in a single item auction, the public value summarization function is actually extremely simple, right? It's just 1 if you get the item, and it's 0 if you don't get the item. So let's think about the natural auction that's induced by the monotone choice rule we get when we say, I'm just going to give the item to the person who reports the highest bid. Right? That's a monotone choice rule. So then what happens as we consider the counterfactual in this integral and ask, what would happen if you bid $0 and then slowly raised your bid up to VI dollars. Well, for a while, you would not be the high bidder, right? You would lose the auction probably if you bid $0. And so for a while, the value that we're integrating over is just 0. And then at some point, at some point, Z will cross some threshold and you will become the high bidder. And all of a sudden, this term will evaluate to 1. And what is the threshold at which you become a high bidder? Well, it's exactly when Z crosses the reported bid of the second highest bidder, right? So suppose VI prime is the value of the second highest bidder. Let me see if I can annotate the slide. So, there's going to be some value VI prime at which, as soon as you bid above VI prime, the value of the second highest bidder, you become the high bidder. And so this term that we're subtracting off is going to be the integral from VI prime to VI of 1, right? Because the public value summarization function is 1 whenever you are the high bidder and 0 otherwise. And this is just VI minus VI prime. Okay? And so the amount that we ask you to pay, if you ended up being the high bidder when you bid truthfully, is, well, VI your bid minus VI prime, which is just VI prime. VI prime. So in the case of a single item auction, this complicated, payment rule ends up just exactly being the sort of simple second price auction rule that we talked about last class, right? In that case, it corresponds to saying, if the high bidder is the winner according to our choice rule, then the amount he has to pay is equal to the bid of the second highest bidder. And this, complicated looking payment rule viewed that way is just a generalization of this rule that we talked about last time, in which we ask the high bidder to pay the second highest bid, right? And it sort of makes sense if you think about it, right? Like, the reason that in general you might not bid truthfully is because you might worry that if you bid truthfully, there would be some other, possibly lower bid that you would regret not having made, right? Like, maybe if you win and you're the high bidder, maybe like you could have bid lower and still won the item, but paid less. And this payment rule is sort of, insurance against that. It's saying that I'm only going to charge you sort of the amount that will cause you not to regret any lower bid. Okay, so maybe that's a little piece of intuition here. Okay. So let's prove it, and just so that our notation is a little bit less cumbersome, I want to simplify it a little bit here. Okay. So first, what exactly is it that we need to prove when we prove that a mechanism is dominant strategy truthful? We need to prove that for every bidder I, they cannot improve their utility by deviating and bidding something else, no matter what everyone else does. And so throughout the whole argument that we're going to make, we're going to be fixing some bidder I, right? Because we have to make this argument for everyone. And we're going to be fixing some vector of other bids, V minus I, because we have to argue that truth-telling is a best response, no matter what everyone else is doing. Okay, so let's just avoid having to write I and V minus I over and over again, and we'll fix some particular agent I, and we'll fix some vector of bids of all of the other agents. Okay, and I'll just write V for VI, since now there's only one agent that we're talking about. And instead of writing W of x of v, the value of bitter i's public value summarization function for the alternative chosen when he bids vi and everyone else bids v minus I, I'll just write all of that as y of v. This is just the bitter i's unscaled utility, unscaled value for the alternative that's chosen as a function of his own bid v. Right? Like once I fix everyone else's valuation functions, now from bitter i's perspective, he can think of the alternative that the mechanism chooses as just a function of his own reported valuation, and the optimization problem he needs to solve when deciding what to bid is just what bid v is going to optimize his utility as a function of y of v. Okay, so just a notational switch to save ourselves some subscripts. Right, so again, just to instantiate this in the case of single item auctions to make sure that this notation isn't becoming too abstract and we're grounded. For a single item auction, right, we would now write y of v equals 1 if bidder I gets the item when he bids v, if v is a sufficient bid for him to win, and y of v equals 0 if when he bids v, he loses the auction. Okay. Okay. And we have two things to prove here, right? Because we're claiming that monotonicity is a complete characterization for truthfulness, right? We have to prove both directions of this claim. And I want to start with the backwards direction. So first, what I want to do is I want to assume that the payment, I want to assume that the choice function x is monotone non-decreasing. And starting from that assumption, I want to prove that the payment rule that we wrote down on the last slide actually does make the auction dominant strategy truthful. Okay, and after we prove this, we'll have to prove the sort of seemingly harder, less concrete thing, which is that if the choice rule is not monotone, then there doesn't exist any payment rule, not just the one we gave, but no payment rule at all that makes the auction truthful. Okay, so right, like in this direction, we're proving something sort of concrete that we can hope to prove just by calculation, that if you have a monotone choice rule and I plug in, verbatim the payment rule from the last slide, then nobody can ever benefit by misreporting their valuation function. Then we'll have to prove sort of the seemingly more difficult, less concrete forwards direction afterwards. Before we jump into the proof, are there any questions about the setup here? Okay. So let's start just by remembering what it is we're supposed to prove, right? Like we want to prove that bidder I cannot benefit by any deviation. So we need to show that if he bids truthfully, his utility will be higher than it would be if he misreported his valuation function for any other, misreport v prime. Okay. So let's just write that down. Well, what is bidder I's utility if he bids truthfully? Right? It's his value for the alternative chosen minus the payment that he has to make, given that he bids truthfully. So that's what we have on the left-hand side here. His value for the alternative chosen is just v times y of v. Right? Here we're using the fact that this is a single parameter domain, and everything except the scaling v of his valuation function is sort of wrapped into this public value summarization function y. Okay, so the alternative chosen evaluates to, the value summary y of v. And if bidder i's true valuation is v, his value for the alternative chosen is v times y of v. On the other hand, we're going to ask him to make some payment, and so his utility is less by the payment that we ask him to make when he bids truthfully. On the other hand, he could misreport his valuation to the mechanism. He could report v prime instead. Okay, and what would happen if he did that? Well, on the one hand, a different alternative would be chosen, right? And that different alternative would evaluate to a different value of his value summarization function, y of v of prime instead of y of v. On the other hand, misreporting his valuation, right, it's a lie. It doesn't actually make him value the alternatives any differently. And so his true valuation for the alternative chosen isn't v prime times y of v, it's v times y of v, because his true valuation really is still v. Okay, so if he lies, a different alternative will be chosen. His value for that alternative will be v times y of v prime, right? He changed the alternative that was actually chosen because of the lie. And he also potentially changed the amount that we asked him to pay. Right? Instead of having to pay p of v, he'll now have to pay p of v prime. Okay. And what dominant strategy truthfulness requires is that the left-hand side, the utility that he gets if he bids truthfully, should always be higher than the right-hand side, the utility that he gets if he lies, no matter what lie he makes. Okay, so, remember I claimed that this direction was sort of mechanical because I already told you what the payment rule was, right? So we need to verify this inequality here, and we can plug in the payment rule that we specified as part of the theorem. So remember, what was the payment rule? Well, the payment rule was just the bidder's reported valuation for the alternative chosen minus this integral from 0 to the reported valuation of the bidder's public value summarization function, right? So when we subtract off the payment, on the left-hand side, when the bidder has bid truthfully, right, we had the payer's value for the alternative and we subtract it off because the first term of the payment rule is just the buyer's value for the alternative. And then we add in this integral from 0 to v of the public value summarization function at the variable we're integrating over. On the other hand, on the right-hand side, we don't get the same nice cancellation that we're going to get on the left-hand side because on the one hand, the buyer's true valuation for the alternative that's chosen is v times y of v prime, right? Because y of v prime summarizes his reported valuation for the alternative chosen, his valuation for the alternative chosen as a function of his lie, v prime, but he really still values things according to v. And so his true valuation for the alternative chosen when he lies is actually v times y of v prime, but the payment rule doesn't know that, right? In the payment rule, we subtract off his reported valuation for the item, which is v prime times y of v prime, right? And then we have to add back in this integral, which is now an integral not from 0 to his true value, but an integral from 0 to his reported value. Okay, so nothing's happened here except we've just sort of plugged in verbatim the payment rule that was defined in our theorem for P of V and P of V prime. Okay, and now we can do a little bit of rearranging, right? So first we can observe that we get this nice cancellation on the left-hand side, right? Bidder i's valuation, v times y of v, exactly cancels out with the first term in the payment rule, which corresponds to his reported valuation. And of course, when the bidder bids truthfully, those two things are the same. And so on the left-hand side, all we're left with is this integral from 0 to v of y of z. And on the right-hand side, we have this similar integral, this integral from 0 to v prime of y of z, but we didn't get the cancellation that we got on the left-hand side because there was this difference between the true valuation and the reported valuation. And so, we can combine these two terms, right? They're both in terms of some number times y of v prime, and we just see that what we're subtracting off is v prime minus v, the difference between the reported valuation and the true valuation, times y of v prime, the value summarization function evaluated at the lie. Okay, so all we've done is we've plugged in the payment rule, and we've done a little bit of algebra to sort of cancel terms on the left and combine terms on the right. Okay, and remember, just sort of keeping stock of the whole plan, we started with this inequality on the top. Right? This is the thing we want to show. We don't know that this is true. And we plugged in the payment rule and we simplified. Okay, so, the top inequality, this thing we want to show, is true if and only if this bottom inequality, what we sort of reduced to, is true. And so what we need to prove is that this inequality here at the bottom is always true for every pair of values v and v prime. Okay, so we just need to show that like this thing at the bottom here is like an identity under the assumption that y is a monotone function. Okay, and there's going to be two cases here corresponding to whether v prime is bigger than v or v prime is smaller than v. Right? The two cases are going to correspond to whether when you lied to the mechanism, you lied and said that your value was too big, or you lied and said that your value was too small. And that'll sort of correspond to whether we're subtracting something off here or adding something here, right? Because v prime minus v could be positive or negative. Okay, so in the first case, v prime is bigger than v. This is the case in which the lie that you told was that your value was actually higher than it is. Okay, and I have some algebra here, but I actually want to, if I can annotate the slide, just sort of convince you of this by picture. Okay, so if v prime is bigger than v, then a natural thing to do is to subtract the integral on the left-hand side from both sides, and what we'll be left with is an integral ranging not from 0 to v prime, but from v to v prime. Okay, and we'll need to show that this integral is smaller than something. Okay, so when we just sort of do that manipulation, we find that the thing that we need to show is that the integral from v, the smaller value, to v prime, the larger value, of this monotone value summarization function is less than v prime minus v, which is a positive number because v prime is bigger than v, times y of v prime. Okay, so let's draw a picture to convince ourselves of that, if we can. All right, so we've got, some axes here, and we've got maybe two numbers. We've got v and we've got v prime. Okay, and we know v prime is bigger than v. And we've got this function y that we're integrating from v to v prime. Now, we don't know too much about y, but we do know from the assumption of the theorem that y is some monotone function. So whatever y looks like, it is increasing as we go from v to v prime. Okay? And on the left-hand side, we have the integral of this function, which, as you will remember from your kindergarten calculus class, is just the area under the curve. Right, so the integral of this curve of y of z integrated from v to v prime is just the area under this curve. Okay, so that's the left-hand side. It's the area under this curve that's monotone increasing. On the other hand, what's the right-hand side? Well, the right-hand side is the product of two numbers, and so that's just the area of some rectangle. right? And so let's just figure out what that rectangle is. Let's see if I can draw in another color here. So right up the right-hand side, right, like what's the area of a rectangle? It's base times height. So let's say the base is v prime minus v, which is just, this is just this interval here between v and v prime. And what's the height? Well, the height is y of v prime, which is just the smallest value that this curve takes, the value that this monotone increasing curve takes all the way on the left, all the way on the right at v prime. It's the largest value that this curve takes, right? So y of v prime is this point up here. That's the height of our rectangle. And so the right-hand side is the area of this rectangle, this red rectangle, whose base is v to v prime and whose height corresponds to the rightmost point on this curve, which is the largest value of the curve because by assumption, y is monotone increasing. Okay? And so we can see that the area of the rectangle is larger than the area under the curve because the curve is increasing, and we took the height of the rectangle to be the largest value of the function. Okay, and that's actually exactly what we wanted to show, right? That the right-hand side, the area of the rectangle, is bigger than the left-hand side. Okay, so that's it for case number one, right? In case number one, when v prime was bigger than v, we sort of started from the definition of dominant strategy truthfulness, and we manipulated it into this form here, so that if we could show that for every v prime and v, this inequality always holds, then our mechanism is dominant strategy truthful. And it turned out that this inequality holding just corresponded to the area of the rectangle being bigger than the area under the curve, which we can see is true. Okay, so in case one, when the bidder's lie, the bidder's misreport is bigger than his true value, we're done. We've shown that you can never benefit by reporting a value that's higher than your true value. Okay, and so we've got one remaining case, which is case two. What happens if your misreport is smaller than your true value? Okay, so just going back a couple of slides to the thing that we need to show, right? We need to show that this inequality always holds. And the case that we're considering now is when v prime is smaller than v. And of course, the natural algebraic manipulation to do now is to subtract off, this integral from both sides, right? Since v prime is smaller than v, when we subtract this off from both sides, we will get, on the left-hand side, the integral from v prime to v of y of z, right? The area under this curve, which we now are going to need to show is bigger than something. Okay? So let's try to do this also with a picture. Okay, so when v prime is less than v, when you shade your bid downwards, then what we need to show is that this integral, right, of y of z, but now integrating from the smaller value v prime to the larger value v, is bigger than v minus v prime times y of v prime. But again, I claim this follows from sort of a similar picture. So again, let's draw our picture. Okay, we've got our axes, and again, we have two values, but this time v prime is the smaller of them, v prime, and v is the larger. And we don't know too much about this function y, except that whatever it looks like, it's monotone. Okay, now again, the left-hand side, this integral is the area under the curve. Okay, and again, the right-hand side is a rectangle, and the base of the rectangle is v minus v prime. Okay, it's the still the interval between v and v prime, and the height of the rectangle is now y of v prime, which is now the smaller of the two values, right? Because v prime is smaller than v, and y is monotone increasing. So y of v prime is actually the smallest value on this curve. And so the rectangle now lies strictly under the curve, right? And so now things are reversed, right? In this picture, the area of the rectangle is smaller than the area of the curve because the rectangle is entirely contained within the curve. But again, that's exactly what we wanted to show. This time that the area of the rectangle was smaller than the area under the curve, which again, we can see in this picture, or you can derive in a couple of lines of algebra. Okay, and so sort of a geometric argument, but that establishes the first direction of the theorem, right? Like that establishes that if your choice rule is monotone, if the algorithm that you want to implement is corresponds to a monotone choice rule, then if you want dominant strategy truthfulness, like you don't have to be clever, beyond whatever cleverness it took you to come up with the algorithm, right? Like once you come up with a monotone algorithm, then you can just read off this payment rule that accompanies the theorem, and no matter what your algorithm was, so long as it's monotone, this payment rule makes it truthful, right? That's what we just proved. Okay. And so there's just one more thing to prove. It's the other direction of the theorem, which is the seemingly harder direction because, we have to argue about not just one payment rule, but all possible payment rules. But actually, as we'll see, isn't so hard. So what we need to prove, remember, is that if the algorithmic problem you want to solve corresponds to a choice rule that is not monotone, then it cannot possibly be the case that any payment rule you come up with will make it dominant strategy truthful, right? We need to show that, equivalently, right? We can show the contrapositive. If you present to me some mechanism, right, which is a choice rule and a payment scheme, and you assert to me that this mechanism is dominant strategy truthful, then it's enough for me to demonstrate that your mechanism must have a monotone choice rule, right? And maybe think about that for a moment, that those two things are equivalent. Sort of the most direct statement of what we want to show is that if your choice rule is not monotone, then there's no payment rule you can come up with that will make it truthful. But equivalently, we can show that if, by some fortunate circumstance, you came up with a payment rule that makes your mechanism truthful, then it must be that your choice rule was monotone. Okay, that's the contrapositive, and that's what we're actually going to prove. And so let's try to figure that out. Let's fix any two numbers, v prime and v. Okay. These are two numbers, they're not the same. And so without loss of generality, let's imagine that v prime is the bigger of the two numbers. Okay, v prime is bigger than v. And so, our only hypothesis here is that the mechanism that you gave me corresponding to your choice rule and your payment rule was truthful. And so let's try to get as much out of that hypothesis as we can. So we're sort of primed to think of v as your true valuation and v prime as your misreport. So let's first figure out what truthfulness implies in that setting, right? If your mechanism is truthful and my true valuation is v, then it had better be that I cannot benefit by misreporting my valuation upwards. So it had better be that if I report v And of course, if I do so, I will get utility equal to v times y of v, my valuation for the alternative chosen by your mechanism, minus p of v, the amount your mechanism asks me to pay, right? This is how happy I am if I report truthfully. It had better be that whatever that is, it is only bigger than my utility if I lie and report v prime. And what's my utility if I lie? It's just v times y of v prime, my valuation for the alternative actually chosen, minus p of v prime, the amount you asked me to pay, right? Like truthfulness just says, there's no misreport that can improve my utility. Here I just have fixed some particular misreport v prime, and I've observed that truthfulness implies that I had better not be able to benefit with that misreport. But we can also flip things around, right? Because if a mechanism is truthful, that means that you can't benefit by deviating no matter what your valuation is, right? You shouldn't be able to benefit by deviating if your valuation is v, but also you shouldn't be able to benefit by deviating if your valuation is v prime, right? Like when we design the mechanism, it has no idea what your valuation is. The mechanism has to guarantee that nobody can benefit by misreporting their valuation no matter what their valuation is. And so let's pretend for a moment that your valuation is not v, but is instead v prime. It had better be that the mechanism also implies that if your valuation is v prime, you cannot benefit by lying and reporting that your valuation is v. And so we also get this other inequality in terms of the same two quantities, v and v prime, right? In this thought experiment, your valuation, your true valuation is v prime. And so if your true valuation is v prime, then your utility, if you report v prime, is equal to the left-hand side here, right? It's your true value for the alternative that's chosen when you report v prime, which is now just v prime times y of v prime, minus the amount you're asked to pay when you report v prime, which is p of v prime. And we know that this utility has to be higher than the utility that you would get if you lied, if you misreported, right? And if you it has to be higher than it would be if you misreported anything, in particular if you misreported v. And if you misreported v, your utility would be v prime times y of v, minus the amount we ask you to pay, p of v, when you report v, right? And so we also know that the left-hand side here has to be higher than the right-hand side here. Okay, so on the one hand, these two inequalities are sort of direct consequences of the definition of dominant strategy truthfulness. But on the other, maybe they're just a little bit subtle, so I just want to make sure that we understand them, right? And they're taking advantage of the fact that dominant strategy truthfulness is a guarantee simultaneously for all possible bidders, right? Like when you're designing the mechanism to be dominant strategy truthful, and when you're stating that the mechanism is dominant strategy truthful, you don't know what people's valuations are. And so the statement is really that no matter what your valuation is, there cannot possibly be any benefit by deviating. And here we're taking advantage of the fact that that is true if your real valuation is v and you're considering lying and reporting v prime. But it's also true at the same time if your real valuation is v prime and you're considering lying and reporting v. Okay, is that clear why dominant strategy truthfulness can actually give us these two inequalities and not just one? Okay, and when we have two true inequalities, it's really tempting to do the obvious thing, which is to add them together. And something really nice happens when we add them together, which is that some terms cancel. In particular, all of the payment terms cancel, right? In the first inequality, on the left-hand side, we have this p of v term, which is the same term that we have on the right-hand side of the second inequality. Similarly, in the first inequality on the right-hand side, we have this p of v prime term, which is the same term that we have on the left-hand side of the second inequality. And so when we add these two inequalities together, all of the terms corresponding to the payment rule are going to cancel out, which is actually exactly what we want. Because remember, in the end, we're trying to prove something that is independent of the payment rule, right? That this is how we're going to accomplish this seemingly difficult task of being able to show that there's no payment rule whatsoever that can make a non-monotone mechanism truthful, right? We're going to add these two inequalities up, which, each of them crucially depends on the payment rule. Dominant strategy truthfulness is really, just as much a function of the payment as it is of the allocation rule. But what we're going to end up with is a single inequality that depends only on the allocation rule, right? So when we add these two inequalities up, we get the following inequality that depends only on the allocation rule, right? And it holds for any pair v and v prime such that v prime is bigger than v, right? We get that, let's just remember where these terms come from. V times y of v plus v prime times y of v prime is bigger than v times y of v prime plus v prime times y of v. Okay, that's what we have here, just adding the two inequalities that we got from dominant strategy truthfulness. And we can rearrange to combine terms, right? Like there's two kinds of terms here. There's terms that involve y of v prime, and there's terms that involve y of v. And so we can sort of aggregate them together, right? So on the left-hand side, we're going to get v prime minus v times y of v prime, right? And on the right-hand side, we're going to get v prime minus v times y of v. Okay, so again, just sort of remembering where we are in the argument, we started from some scheme, some allocation function paired with a payment rule, and the only thing that we knew about it is that it was dominant strategy truthful. And what we've gotten is we've gotten some inequality that we know must hold about the allocation rule. Okay, and remember that v prime is bigger than v, right? Like we assumed without loss of generality that v prime was the bigger number. And so that means that we can divide both sides by v prime minus v, right? V prime minus v is not 0, first of all, so it makes sense to divide both sides by it. And it's also positive. It's a positive number. So when we divide by v prime minus v, the inequality is not going to flip, right? We can divide by v prime minus v, which appears on both sides, and cancel these terms out. And what we end up with is that y of v prime has to be bigger than y of v, right? And remember, the only thing we assumed was that v prime was bigger than v. So the implication that we've derived is that if v prime is bigger than v, then y of v prime has to be bigger than y of v, which is exactly the condition we need. That is the monotone non-decreasing condition for these choice rules. Okay, so what we've proven is that if your mechanism is dominant strategy truthful, then your allocation rule must be monotone. And by contrapositive, if the function, if the algorithm that you are hoping is going to be your allocation rule in a dominant strategy truthful mechanism is not monotone, then you're out of luck. There is no possible payment scheme you can pair it with that will make it dominant strategy truthful. Okay, so that's it for today. We've now fully characterized the set of choice rules that can be implemented with dominant strategy truthfulness, at least in this restricted setting of single parameter domains. And what I'm going to do next class is think about how we can address this other failing of the VCG mechanism, which is that it's not necessarily computationally efficient. Okay, so I'm going to stop the recording now.